All right, mathletes, here we are looking at compound events and using two-dimensional grids to help us solve those compound or combined events. Okay, so combined events, and when we're looking at two or more events. Okay, and we call these compound events. Two events are called independent if the occurrence of each event does not affect the occurrence of the other. Okay, and two events A and B are independent, then the probability of A and B happening equals PA times B. So because we're multiplying the probability of A times the probability of B, that's when this idea of two-dimensional grids can play into helping us problem solve. So let's say if we're talking about flipping a coin, okay, and then also using a spinner where they have numbers 1 through 3, okay, we can call this event A, the coin flip, and we can call this event B being the spin. So if we're thinking about an area model or a two-dimensional model, okay, where this is event A, so the coin could be a head or a tail, okay, and the spinner is 1, 2, or 3, we can see how we get all our possibilities, and our two possibilities times our three possibilities gives our total of 6 possibilities. So that can be how we use our two-dimensional grids for problem solving. So looking at an example here, two square spinners each have 1, 2, 3, and 4 on their edges, are twirled simultaneously. Draw a two-dimensional grid of the possible outcomes. So we can see spinner 1 getting a 1, 2, 3, or 4, and spinner 2 getting a 1, 2, 3, and 4. Okay, so we can see by multiplying here we have 16 total possible outcomes. Okay, so if we want to look at determine the probability of getting a 3 with each spinner. So getting a 3 with each spinner, okay, is represented right here. Okay, where it's a 3 the spinner 1, 3 in spinner 2. Okay, so to find the probability, I just have one outcome, okay, out of the 16 where I get a 3 with each spin. Okay, so for number 2 here, getting a 3 and a 1. So a 3 and a 1 happens two ways. I could get a 3 on the first spin and a 1 on the second spin, so that's there. Or I could get a 1 on the first spin and a 3 on the second spin, and that happens right there. So my probability, I can see I have 2 successes there out of my 16 total outcomes. So this can be simplified to 1 out of 8 as my probability of getting a 3 and a 1. Okay. And for our third question here, an even result with each spinner. Okay, so an even result with each spinner, well, I could spin a 2 on the first one and a 2 on the second one. I could spin a 2 on the first one and a 4 on the second one. I could spin a 4 on the first one, a 2 on the second one, and a 4 on the first one and a 4 on the second one. So I see I have 4 possible outcomes of my 16. I simplify my fraction and I see that this is a 1/4 probability of getting that outcome. So you can see how we can utilize a two-dimensional grid to help problem solve with figuring out our compound events here. These two events being independent, because what I spun on spinner 1 is not going to affect what I spun in spinner 2. Okay, it doesn't have a memory on the spinner. Okay. 3. A cone and a die are tossed simultaneously. Determine the probability of getting a head and a 3. Okay. So again, if I think about a coin, okay, I can label here and say head, tail, okay, and I could get a 1, 2, or a 3 on my spinner. So I have 1, 2, 3, 4, 5, 6 outcomes. So determine the probability of getting a head and a 3. head and a 3 happens once. So that's 1 out of 6. Okay. I could also use my formula here and multiply my probabilities. So probability of a coin getting a head is 1 out of 2. Okay. Multiply by the probability of getting a 3 on my spinner. Okay. Well, that's a 1 out of 3. When we multiply this across, we can see that this is 1 out of 6. Same solution we got from our grid here. Okay. Let's look at another example here. 4. So Sunil has a probability of 4/5 of hitting a target, and Monica has a probability of 5 out of 6 of hitting that same target. They both fire simultaneously at the target, determine the probability they both hit. Okay, so using that multiplication principle established by the two-dimensional grids, I can just multiply my two probabilities here. Okay, and they're independent events because Sunil and the Monica are shooting at the same time, so whether they don't know if the other one's going to hit it, and that probability is not going to change. So if we do 4/5 times 5/6, this is going to be equal to 20 out of 30, which is a 2/3 probability. They both hit. Okay, so if they both miss, okay, so remember for a complement, if Sunil's probability of Sunil hitting is 4/5, the probability of Sunil not hitting is going to be the complement, so I do 1 minus 4/5, which is 1/5. And using that same logic for Monica, the probability of Monica hitting was 5/6. So the probability of Monica missing is 1/6. Okay, put the little knot there. So then for this one, they both miss is going to be 1/5 times 1/6, which equals 1 out of 30. Okay, notice that these two do not add. Do not add to be 1. Well, why is that? Well, you could have where Sunil hit and Monica didn't, and you could have the vice versa where Monica hit and Sunil didn't. So we're still missing some outcomes here, but this is how we could find for if they both miss, they both hit, and our final probabilities for 1 and 2. Okay, so other things we're going to talk about are dependent events. Okay, compound events that do depend on each other. So if A and B are dependent, then the probability of A and B equals probability of A times the probability of B given that A occurred. Okay, the occurrence of one event does affect the occurrence of the other. So that fact that it does affect, that really is our definition of dependent. Okay, so suppose a hat container has 5 reds, 3 blue tickets. Okay, one ticket is randomly chosen in color is noted, and it is then thrown away. Okay, so this idea that it's thrown away and it's not returned into the basket is going to change our probability of picking the next ticket. So notice, picking a red ticket right away, a second ticket is stolen. I learned what is the chance that the second ticket is red. Okay, so before we had 5 out of 8 for it being equal to red. Okay, one of those red tickets was picked and it's thrown away. So it's the probability that the second ticket is red. Okay, well remember, now there's only 4 remaining tickets. Okay, and there would be 7 total remaining, so that probability is 4 out of 7. Okay, that's if the first ticket was red. Well, what if the first ticket was blue? Well, now if the first ticket was blue, okay, you still have the 7 tickets left, but you have 1 additional red, so you have 5 out of 7. So these are dependent events because the outcome of these, so notice that 5 sevenths is not equal to 4 sevenths. These events have different probabilities because it mattered, it was affected by what happened in our first ticket selection. Okay, if a red one was changed and a blue one was changed, the probability of getting a red ended up being different. Okay, so let's look at it. Our last example here. A hat contains 20 tickets with the numbers 1 through 20 printed on them. Okay, if 3 tickets are drawn from the hat without replacement, determine the probability that they are all prime numbers. Okay, so this is when it's useful to use set notation. So my universal set is all x's such that x's are from 1 to 20. Okay, and they're just the numbers, so we're saying that x is contained within our natural numbers, our counting numbers, or we could say integers. Okay, so we are wanting to know, let's call our event A. Event A is selecting a prime. Okay, well, A set, so what are the set of prime numbers in our universal set? Well, 1's a prime, 2's a prime, 3's a prime, 4's not, 5 is, 6's not, 7 is, 8's not, 9's not, 10's not, 11's a prime, 12's not, 13's a prime, 14's not, 15's not, 16's not, 17's a prime, 18's not, 19's a prime, and 20 is not. Okay, so those are the elements, okay, that are prime. Okay, so if 3 tickets are drawn from random, what without replacement determine the probability they are all prime numbers? So for our first ticket chosen, we have 20 tickets to choose from. How many prime numbers do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have a 9 out of 20 chance of picking a prime number. Well, for the second chance, you're not replacing it. Okay, so without replacement, that means we're tearing it up, throwing it away. So now we are only dealing with 19 tickets. We're assuming we got one of the primes, so it doesn't matter which one we think it is. Maybe it was this one. Okay, but that's just going to leave us with 8 prime numbers left to pick from. Okay, and now we want to determine for if we pick 3 tickets are drawn at random, they're all prime numbers. Okay, so then from this we do times. Okay, well, we threw that ticket out, so the first 2 tickets, so we're left with 18, and the first 2 numbers were prime. So, and the third ticket, well, now we only have 7 to choose from. Okay, so then we do our multiplication. So 9 times 8 times 7, that's going to equal 504 over 20 times 19 times 18, and we get 6,840. If we wanted to put this as a percentage, it'd be 504 divided by 6,840, and we get approximately, because I'm rounding, 0.074 as our probability of that happening, getting all prime numbers out of all 3 of our selections. Okay, so that concludes our notes tonight. Please highlight any questions and bring them to class.